Welcome everyone to our RAS Public Talk series. This is our last one of the 2021-22 season. Thank you very much for being with us. I'm Philip Diamond, Executive Director of the Royal Astronomical Society, which encourages the study of astronomy, geophysics and space science. I'm honoured to introduce you to our guest speaker, Lord Rees of Ludlow, who will be speaking to us about space exploration and the search for extraterrestrial life with humans and with robots. Martin Rees is the UK's Astronomer Royal. He is based at Cambridge University, where he is a Fellow and former Master of Trinity College. He is a former President of the Royal Society and a member of many foreign academies. His research interests include space exploration, high-energy astrophysics and cosmology. In addition to his research publications, he has written many general articles and 10 books, including most recently On the Future, Prospects for Humanity, and with Don Goldsmith, The End of Astronauts. A quick reminder that there will be a Q&A after the talk, so please get your questions ready. There are places to post your questions for our speaker in the Q&A box if you've joined us on Zoom and in the chat box on YouTube. Thank you everyone for being here, and thank you, Martin, for being with us today. Over to you.
Okay, well, thank you very much for inviting me, Phil, and hello everyone who's listening in. My talk is going to be about space exploration and some speculations towards the end. But I want to start with a bit of history. This is Trinity College, and it looked the same 300 years ago as it does today. And the best student we ever had was this person here, Isaac Newton. And of course, as you know, he went away in 1665 during the plague year, went back to his home in Lincolnshire and had his big idea, or so we are told, under an apple tree, where we shut down our university just last year. The students all went home, they came back, but none with any great ideas, sadly. But Newton thought about gravity, and he must have thought about space travel, because this is a famous illustration from the English edition of his great book Principia. It shows the trajectory of a cannonball fired from a mountaintop. And the faster it's flung, the further it goes. And if it's projected fast enough, then its trajectory curves downwards, no more steeply than the Earth curves away underneath it. It goes into orbit. And this is still, I think, the neatest way to explain to young people the concept of orbital flight. But Newton calculated that to go into orbit, the cannonball has to be fired at about 18,000 miles an hour. Far beyond, of course, what could be achieved by the artillery of his time. And indeed, it wasn't until 1957 when the first object went into orbit. This was the Soviet Sputnik, Sputnik 1, and this was followed by some dogs, and then 4 years later by the first human to go into orbit, Yuri Gagarin. And 8 years after that, we had this iconic picture taken by Ed Anders in Apollo 7 orbiting the moon, and showing the Earth's delicate biosphere contrasting with the foreground moonscape, where just 1 year later, Neil Armstrong made his one small step. And I treasure this picture, signed for me a few years ago by 7 of the Apollo astronauts who had walked on the moon's surface. You've got to be quite elderly to remember when people walked on the moon. And thinking back to that time, which I'm certainly old enough to remember, I thought that it would only be 10 or 20 years more before we had the first footprints on Mars. After all, it's only been 12 years from the first Sputnik to Neil Armstrong. But of course, that didn't happen. The Apollo program was hugely expensive. It used up to 4% of the American federal budget in the 1960s, and its aim was to beat the Russians. And having achieved that, there was no motive for further expenditure. And so it turns out that the Apollo program is still the high point of human exploration of space. And in the subsequent decades, many hundreds of people have been into space, mainly in the International Space Station, but this has just, of course, taken them into low Earth orbit. And it's not very dramatic. And indeed, the space station only makes the news when something goes wrong, when the toilet fails, or when Chris Hadfield, the Canadian astronaut, sang David Bowie songs and played his guitar. But to be fair, they did some important experiments, but mainly on human reactions to extended weightlessness. This was a hugely expensive venture. And of course, the space station is still up there. Well, when will there be, if ever, future inspirational projects involving humans? The next step would obviously be to go back to the moon or to go to Mars. And this is a theme of my new book, which Phil mentioned in his introduction, a book co-written with Don Goldsmith at Berkeley, called The End of Astronauts. And this discusses the case for sending humans into space. Well, during the next few decades, the whole solar system will be explored by swarms of miniaturized probes, following up on the pictures we already have, the familiar ones here, taken by probes that have been to the planets and major moons of our solar system. And the robotic probes that we can send in the next decades will be much more sophisticated than the ones we sent in the past, which were designed in the 1990s. I'm thinking, for instance, of the wonderful Cassini probe, which spent 13 years orbiting Saturn and its moons, or the New Horizon, well, Rosetta, the European probe, which landed a small robot on this comet and sent back pictures of it, or the New Horizon NASA probe, which sent back pictures of Pluto, which is 12,000 times roughly further away than our moon. If you think back to the computers and phones of the 1990s, when these probes were designed, remember they had a 10-year journey before they started their observations, think how much things have changed in microelectronics, etc., how much better we can do today. And that therefore indicates the scope for much more sophisticated probes to be sent to all the regions of our solar system. And the next step in space is going to be the deployment in space of robotic fabricators. And these can build large-scale structures, for instance, giant telescopes or solar energy collectors. And the robots will have enough intelligence to do this without humans. So the main point of our book is that the practical case for sending humans into space gets weaker with each advance in robotics and miniaturization and AI. It's far more expensive to send humans, especially on a long journey where you've got to feed them, etc., and be concerned with their safety. And so if robots can do the job, then that's the way to do it. And I'm going to be talking more about this in this lecture. I should mention as a digression that about a month ago, I gave a talk to a far more terrifying audience that I've got today, over 1,000 15-year-olds doing GCSE physics in a big hall in Cambridge, over 1,000 of them. And I started off to lighten things up with 3 questions. I asked them, how many of you would like to go to Mars? About half the hands went up. Then, how many would still go if it was a one-way trip? A few hands stayed up. But then thirdly, is there someone else you'd like to send on a one-way trip? And all the hands went up for that, of course. And another interesting exchange I had at the end of that talk was one of the young people came up to me and said, would you be able to still communicate if you're on Mars with people on Earth? And I said, yes, but there'd be a delay of between 6 and 40 minutes, depending on where Mars was in its orbit. And he thought it was terrible to have to wait so long. Tell that to Captain Scott or Magellan. You know, there's a big change in what people's expectations are of communication. Well, going back to the Apollo program, this was Schmidt and Kernan on Apollo 17 on their moon buggy, and they were the last people to walk on the moon. They came back in the end of 2072, and no one else has been that far since, no human being. But of course, there have been many probes of the other planets, and particularly many probes to Mars. And this was the Curiosity probe, which was launched about 10 years ago. And this has been trundling over a big Martian crater for a very long time. And it was followed up by Perseverance, which landed last year. This was more sophisticated because Curiosity, if it encountered a rock in its path, had to report back to base to get its course reprogrammed. Whereas this Perseverance can work that out for itself. It still can't identify what's a especially interesting bit of geology where it should take a sample, but in 10 or 20 years, one can imagine that a follow-up to Perseverance with AI will be able to identify which particular place on Mars is especially interesting, because remember that we now have AI that can look at, say, 100,000 chest X-rays and pick out better than a human which ones indicate cancer. So in the same way, we can imagine robotic explorers of Mars doing the real science, collecting samples, etc. And of course, doing this hugely cheaper than sending human beings. It's a 200-day journey, and the robot or craft like this happily hibernates on the journey, whereas for a human, you've got to feed them for the journey, and you've got to worry about radiation if there's a solar flare on while they're on their way, etc. Oh, and I should mention that also there are 2 Chinese craft that landed on the moon last year to do similar things to what Perseverance can do. And as I said, the machine learning is advancing fast, so are sensors, but in contrast, the cost and the risk gap between a human and robotic mission remains huge. If you think of NASA's astronaut program ever since Apollo, which has been limited to the space station, but also events like refurbishing the Hubble space telescope, they are constrained by public and political pressure into being very risk averse. For instance, the shuttle was launched 135 times, and there were 2 spectacular crashes which killed the crew. And these were national traumas in America because the shuttle had been presented as safe. They'd sent a woman school teacher up on one of these probes that crashed, and so it was a trauma. But that failure rate, less than 2%, is something which is certainly acceptable to test pilots and to many adventurers, hang gliders, mountaineers, etc. But because of its safety culture, NASA or ESA will confront political obstacles in achieving any grand goal involving human spaceflight within a feasible budget, because they will, I think, have to ensure that the risk is kept very low if they are sending civilians that we are paying for. And that's why I think the future of human spaceflight lies with privately funded adventurers prepared to participate in a cut price program, which is far riskier than Western nations could impose on publicly supported civilians. And for that reason, were I an American, I wouldn't support NASA's human spaceflight program, which is spending at least $6 billion a year. I would argue instead that inspirationally led private companies, Elon Musk's SpaceX, Jeff Bezos's Blue Origin, should front all these missions. And these private ventures, bringing a Silicon Valley culture into a domain long dominated by NASA and a few aerospace conglomerates, have innovated and improved rocketry far faster than NASA or ESA has done. The latest Falcon rocket, for instance, can put a 100-ton payload into orbit, and its first stage can be reused. And even if the risks to humans were high, there would still be many volunteers, even for a trip to Mars, some perhaps accepting a one-way ticket, driven by the same motives as early explorers, mountaineers, and the like. Elon Musk himself has said that he hopes to die on Mars, but not on impact. And he's now, I think, about 50 years old. 40 years from now, he might achieve this. What a way to go. So I think this phrase space tourism should be avoided, because that does lull people into thinking that these ventures are routine and low risk. And if that's the perception, the inevitable accidents will be as traumatic as those of the space shuttle were. So these exploits, when they're privately funded and riskier, must be sold as dangerous sports or intrepid exploration. But I think that by the year 2100, some courageous thrill seekers may have made the 200-day trip to Mars and established some sort of primitive bases anyway, independent of the Earth. But don't ever expect mass emigration from the Earth. Nowhere in our solar system offers an environment even as clement as the Antarctic or the ocean bed or the top of Everest. And here I disagree with Musk and with my late colleague Stephen Hawking. I think it's a dangerous delusion to think that space offers an escape from the Earth's problems. Dealing with climate change on Earth is hard, but it's a doddle compared to terraforming Mars. There's no planet B for ordinary risk-averse people. But we and our progeny here on Earth should, I think, cheer on to brave space adventurers, because they'll have a pivotal role in spearheading what I call post-human future and determining what will happen in the 22nd century and far beyond. This is why these pioneer adventurers in their little settlement on Mars will be ill-adapted to their new habitat, to its gravity and to its atmosphere. So they'll have a more compelling incentive than those of us here on Earth to redesign themselves. And by the end of the century, we will have super powerful genetic and cyborg technologies to modify humans. But these techniques will, we hope, be heavily regulated on Earth. on prudential and ethical grounds. But the settlers on Mars will be far beyond the clutches of the regulators, and they will have the incentive because they're ill-adapted to where they are. And we should surely wish them good luck in modifying their progeny to adapt to alien environments. And this might be the first step towards their divergence into a new species, a sort of post-human species. And if there is one, it's the spacefaring adventurers who will be its precursors. Well, what would they be like? There are chemical and metabolic limits to the size and processing power of organic brains. Maybe we're close to those already, but no such limits constrain computers, still less perhaps quantum computers. So by any definition of thinking, if we extrapolate into the far future, the amount and intensity that's done by organic human type brains will be swamped by the cerebrations of AI. So we are perhaps near the end of Darwinian evolution, but technological evolution of intelligent beings is only just beginning, and it'll happen fastest away from the Earth. I wouldn't expect and certainly wouldn't wish for such rapid changes in humanity here on the Earth, though of course our survival does depend on ensuring that AI on Earth remains benevolent. And organic creatures, even on Mars, will probably need a planetary surface. But if posthumans make the transition to fully inorganic intelligences, which of course is a common science fiction scenario, then they won't need an atmosphere. And they may prefer zero-G, especially if they want to construct massive artifacts. And if they're near immortal, then long voyages through interstellar space wouldn't deter them. So looking far ahead, it's in deep space, not on Earth, nor even on Mars, that non-biological brains may develop powers that humans can't even imagine. I'm often asked, do astronomers bring a special perspective to global issues? And let me explain why I think they do. Most of us are familiar with this time chart of Darwinian evolution, starting maybe 4 billion years ago on the young Earth, which has led to the marvelous biosphere we see around us and of which we're a part. But many people, though familiar with this timeline, tend to think that we humans are the culmination of it, the top of the tree. But no astronomer can believe this. That's because we know that the sun is less than halfway through its life. It'll be 6 billion years before it flares up and engulfs the inner planets. And the expanding universe has a far longer future still ahead of it, maybe infinite. And to quote Woody Allen, eternity is very long, especially towards the end. So we may be nearer the beginning than the end of the emergence of ever greater complexity in the cosmos. Though we are at a critical stage, seeing perhaps a transition from Darwinian evolution to what I would call secular intelligent design, when our descendants can design future beings. And as I say, few doubt that machines will gradually surpass or enhance more and more of our distinctly human qualities. Although we don't quite know how quick this will be. Some people, like Ray Kurzweil, the author of a book called The Age of Spiritual Machines, thinks it'll only be 30 years before the machines completely take over on Earth. The cautious amongst us envisage centuries. But nonetheless, I think the timescale for this advance is just an instant compared to the timescales of Darwinian selection, which led to our emergence. And more relevantly, these time spans for a change in species biotechnology are 1 million times shorter than the time remaining for the Earth before it dies. And certainly, if there's any intelligence around at the time when the Earth dies, it will be very different. So any postcards sent by entities 6 billion years from now, when the sun flares up, they'll be as different from us as we are from a bug or slime mold, thinking thoughts that we can't conceive at all. When one talks about the far future of life and intelligence, there's a big debate about, will these entities be conscious? Philosophers debate this. They debate whether consciousness is special to the wet organic brains of humans, apes, and dogs, or could it be that electronic intelligences, even if their intellect seems superhuman, will still lack self-awareness or inner life? Or is it the case that consciousness would emerge in electronic brains if they're sufficiently complex? There's a debate among philosophers and neurologists about this. Well, some say it's irrelevant and semantic, like asking whether submarines can swim. But I don't think it is. This question of whether robots develop consciousness, I think very much affects how we'll react to the far future scenario I've sketched. If the machines are zombies, then we wouldn't accord their experiences the same value as ours. And the post-human future, dominated by machines, would seem bleak. There'd be nothing to wonder at the beauty of the universe. But if they're conscious, we should surely welcome the prospects of their future dominance. Well, what would be the motives for these posthumans who may eventually spread to the other stars? We've no idea. The ideas are best found in upmarket science fiction. They could be contemplative. Even less obtrusively, they may realize it's easier to think at a low temperature, getting a long way away from any star, or even hibernating for billions of years until the microwave backgrounds cool far below 3 degrees. But of course, they could be expansionist, and this seems to be the expectation of most who've thought about this. But from what I've said, of how far ahead the future stretches, we conclude that even if life had originated only on the Earth, it need not remain a trivial feature of the cosmos. Humans could jumpstart a diaspora whereby ever more complex intelligence spreads through the galaxy, far transcending our limitations. And this could happen via self-reproducing machines, or transmission of DNA, instructions for 3D printers and such like. And the leap to neighboring stars is just an early step in this process. Interstellar voyages or even intergalactic voyages would hold no terrors for near immortal electronic intelligences. And moreover, even if the only propellants used were the currently known ones, this galactic colonization would take less time measured today than elapsed since the Precambrian explosion. And if it proceeded relativistically, it could happen since the advent of primates. Well, this scenario about the far future of life originating on Earth raises the big question, which is the one that we astronomers are most often asked. The question, is there life out there already? Is the galaxy waiting for our remote descendants to spread across it? Are we alone? Well, we don't know the answer to this question. Of course, some people think they do. I get letters from people who say they've met the aliens, they've been abducted by them, etc. And I reply with skepticism. My line would be that if the aliens had made the immense effort to traverse interstellar distances to come here? Would they just meet one or two well-known cranks? Would they just make a corn circle or two and then go away again? It seems unlikely. And so if this letter arrives, I tell these people to write to each other. But the serious question is there life out there? Simple life, even intelligent life. And this topic has become hugely exciting to astronomers in the last 20 years or so. The really hot topic in astronomy is the realization that even though there's no scope we know already for any very complicated life in the solar system, because we would have known about it already, if we look out to the range of stars, then what we've learned is that nearly all of the stars are orbited by retinues of planets, just as the sun is orbited by the Earth and the other familiar planets that we've sent probes to. The first exoplanet was discovered just 25 years ago, and my Cambridge colleague Didier Queloz, he shared the Nobel Prizes for a couple of years ago, and this is his reaction the day he learned he'd won the Nobel Prize. And he's now discovered several hundred more of the thousands of exoplanets we now know about. But these planets around other stars, they're not directly detected by their own light. They are detected by their effect on the star they're orbiting, by their gravity making it wobble, or by the detection of transits. And let me say a bit about this second method. If a planet is orbiting another star and the orbital plane is close to our line of sight, then of course once every orbit it will pass in front of the star and block out a bit of its light. And that's shown here, that if you're looking from a great distance, then the brightness of the star will dip by a little bit every time the planet transits. If you were an alien astronomer looking at the solar system from a long way away, the sun would look an ordinary star, and when the Earth transited across, the star, our sun, would look fainter by about 1 part in 10,000. That's because the Earth's 1% the diameter of the sun, so it's 1 part in 10,000 of the surface area. And so these techniques, if you can detect this small dip in the apparent brightness of the star, can tell you two things. It can tell you how big the planet is, and also the length of the planet's year from the time between successive repetitions of these dips. And the NASA space probe called Kepler spent its first 3 years looking at a field of stars about 7 degrees across and measuring the brightness of over 100,000 stars in that region of the sky with a precision of 1 part in 100,000, and doing this about every hour for each star, looking for cases when you saw dips which occurred periodically. And Kepler found literally several thousand stars which had planets around them. And this tells us that these planets are very common. Most stars have them, but they're not all systems like our Earth. Let me just show you a bit more about one particular system, which was found, in fact, not by Kepler. It was found by Belgian and British scientists using a 22-inch telescope. And that's this object called Trappist-1. This is a system where the central star is an M dwarf star, very faint, about 1% as bright as the sun. And around it is a miniature solar system. 7 planets are detected, and the innermost one is so close to its star that its year lasts 1.5 of our days. And even the outermost one has a year that lasts about 2 of our weeks. But because the star is so faint, the temperature of the 3 outermost planets of these 7 is such that water can exist. This is thought to be a definition of a habitable zone where life could in principle exist. And so on these planets, there could in principle be life. For some reasons, we don't expect this because there'll be lots of flares from this star, etc. But in principle, there could be. But actually, if there were life on one of these stars, it would be in a very different environment because since everything is so close, the planets are tidally locked. So they would present the same face to the star, just as the moon presents its same face to us on the Earth. And so if you lived on one of these outermost planets, you'd have one hemisphere in perpetual daylight and one hemisphere in perpetual darkness. So I guess everyone would live in one hemisphere, except to be a kind of apartheid where the astronomers were the only ones in the other hemisphere. But I should mention that the data here is very good. This is data obtained from the Spitzer telescope of those dips. This is accumulated data, and you can see there's no doubt whatever about the existence of these dips, from which you can infer the sizes of those 7 planets as well as their orbital periods. So we have very good data like this on dozens of other stars. Well, it's a bit frustrating, though, that we can detect these planets indirectly, but we can't actually see them. We only see their effects on their parent star. But in principle, with a sufficiently big telescope, we could do that. And let me take as an illustration, supposing that there were aliens looking at our solar system with a very big telescope, then the sun would look like an ordinary star, and the Earth would look, in Carl Sagan's nice phrase, as a pale blue dot, very close in the sky to its star, our sun, but millions of times fainter. But if the aliens could detect the light from that pale blue dot, they could infer quite a bit about it. For instance, they could notice that the shade of blue would be slightly different depending on whether the Pacific Ocean or the landmass of Asia is facing them. So they could infer that there were continents and oceans, they could infer the length of our day, and they could probably infer something about our climate and our seasons. And by taking a crude spectrum, they could infer what our atmosphere was made of. They could perhaps infer that there was lots of green stuff on our planet from chlorophyll features in the spectrum. Well, we can't do that yet, but there's a hope that in the next decade, we'll be able to get information of that kind about Earth-like planets around some of the nearest stars. And this is just to remind us that we know that most stars have planets around them, and about 1 in 6 has a sort of Earth-like planet in the sense of something the size of the Earth, which is in the habitable zone. Well, as regards detecting the light from an Earth-like planet, our hopes lie in the European Extremely Large Telescope on the Mount Nomenclature for this marvelous machine being built in Chile at the moment, which will have a mirror 39 meters across. Huge. Not one sheet of glass, but a mosaic of 800 bits of glass. And with the right spectrograph, this should be able to collect enough light from planets orbiting stars to make the kind of observations which I just imagined in the case of aliens looking at the Earth, to infer something about the atmosphere and the topography of a planet like the Earth. And we may actually, before the ELT, get some information from James Webb, which of course doesn't have such a big area, but has the advantage of observing in the near infrared. So this is going to make observations. One of my colleagues is part of a team that's going to look for so-called water worlds, planets that are covered in water. So we learn something exciting about planets within the next couple of years from James Webb telescope. Okay. Well, I talked about habitable planets, by which I meant planets like the young Earth, which had water and temperature where water doesn't boil away or stay frozen. But of course, that doesn't mean inhabited. We don't know how likely it is that life evolves, even given the right conditions. We know it happened here on Earth, but it's surprising when people are told that we don't understand the origin of life. We understand Darwinian evolution from simple life to the biosphere that we're part of, but the transition from complex chemistry to the first reproducing, metabolizing entity we call alive, that's still a mystery. Theorists are working on it, we don't know. So it could be that simple life is unique to the Earth. On the other hand, it could be ubiquitous. But even if simple life is common, then complicated life may not be, because we can imagine all kinds of contingencies which could have prevented intelligent life emerging here on the Earth. It might have depended on when the dinosaurs got wiped out and things like that. So even if simple life is common, the kind that can be detected spectroscopically, alien intelligent life, which is what most of the public are most excited about, is something whose likelihood we can't predict. But that's, of course, the thing which is most exciting to us. And we shouldn't be too optimistic, but I just want to spend my last 5 minutes or so talking a bit about the possibility of detecting intelligent life. There are these so-called SETI programs, searches for extraterrestrial intelligence, which are looking for some transmission which is manifestly not natural, or some physical artifact. These are a worthwhile gamble because success in the search would carry the momentous message that concepts of logic and physics weren't limited to human skulls. And in fact, this program has been boosted in the last few years by a Russian investor in California called Yuri Milner. He's pledged $10 million a year for 10 years to expand SETI searches by his so-called breakthrough initiative. And I would say it's far better he should do this than spend the money on a yacht or a football team. And the projects being supported are to buy time on big radio telescopes and to develop special purpose instruments to look for time varying signals, narrowband signals, etc., in both the radio and the optical. And also to look a bit harder for any strange artifacts in our solar system, which if you've seen 2001 movie, you realize could have been left by some kind of intelligence. So we don't yet know how likely it is that there will be anything, but of course, I think most people think that it's worth these modest funds to actually see if we can detect any evidence. Well, what would be the reaction? Of course, it would be, as we all know, hugely important if we did detect evidence for alien intelligence. First, let me say what we would be likely to find. We wouldn't, I think, expect to find a civilization flesh and blood like ours. And the reason for that is this: that if you imagine that there was another planet like the Earth, which had evolved in the way the Earth had done, then for the first 4 billion years, there'd be no evidence of technology. Then there would be evidence of technology of the kind that we're now producing, radio signals and all the rest of it. But that may last only a few thousand years. because as I've indicated, that flesh and blood civilization may be taken over by machines within a few thousand years. And then the machines could perfectly well exist for billions of years more. So if there was another planet like the Earth, on which life had evolved more or less like on the Earth, it's unlikely that it would be synchronized in time to the extent that we would observe it in the few millennia, just a sliver of time, where it's dominated by a flesh and blood civilization. If it lacked, there'd be no evidence for intelligence. On the other hand, if it had a head start, because it was a planet around an older star, for instance, then it would long have passed that stage. And what we would detect would be electronic entities, which are remote descendants of the first technologically advanced creatures on that. So my suspicion is that if we were to detect anything, it would be some electronic entity, maybe not on a planet, but which was perhaps the descendant of entities created by a flesh and blood civilization which has long died out. Well, let me stop there, but just make one final point, which is about how we would react to all this. I think everyone would be fascinated to find aliens, but of course, if these SETI projects fail, then it allows us to be less cosmically modest, because it may then mean that we humans are very special. It may be that the odds against a planet developing life which is able to evolve to the complexity that it had on Earth, that could be very unlikely, and it could be that we on Earth are unique. And if that's the case, we can be less cosmically modest, because we are, though on a tiny Earth, very special. And moreover, if the far future scenarios that I've discussed are possible, then what happens in the next century or two, whether we flourish or wipe ourselves out at this stage, could make the difference between whether the galaxy eventually is seeded by descendants of humanity, or whether it remains sterile. So the stakes are very high if we think that we are unique to the Earth. But these are speculations. And let me just finish with two maxims, which I think are important for everyone who works in this field. The first is that absence of evidence is not evidence of absence. So we can't dogmatically say the light's not out there. And the second is that extraordinary claims require extraordinary evidence. So we're going to need lots of convincing before we really think there is some life out there. So with that, let me stop and hope I've stimulated some discussion. So thank you very much, everyone, for listening.
Well, thank you so much, Martin, for a really fascinating and thought-provoking lecture. You have indeed stimulated many questions. We have about 10 minutes for discussion, so I won't be able to cover them all, but I will do my best to pick out as many questions as I can for you. There are two questions, one from Ben and one from my colleague Lucinda, about whether what you have said implies the end of astronauts. I think everybody has a sort of romantic notion about them, and I think that there would be some sadness, I think, if that, as a profession, as Ben called it, were no longer to be or to aspire to be.
Well, two things. First, of course, I can't make any predictions more than 50 years ahead, but what we do say in our book is that on that time scale, we do think that the human spaceflight exploits should be left to privately funded ventures, leave it to the billionaires, and that's because the practical need for them, for science or for any use of space like communications, etc., can be better achieved by robotic fabricators. and also because the private funders can accept higher risks than NASA or ESA can inflict on the public. So there's no practical need. It's just an adventure, and it should be left to millionaires who can fund it and launch the kind of people who can accept high risks.
Thank you, Martin. I have a question here about technology, rocket technology. Do you think that there will ever be a replacement for the chemical rocket engine by something more futuristic that would open the door for true space travel, like in the TV series The Expanse, which is not one I'm familiar with, and I'm not sure whether you are?
Yes. Well, I mean, I think it's certainly conceivable that there will be some sort of nuclear fission or fusion kind of rocket engine, which can provide maybe a low thrust for a long period, which can speed up the average speed on a long journey. So I think that's feasible. I won't say anything about the time warp and more exotic ones you read about in science fiction, where you can exceed the speed of light by going into a wormhole. But I think it would be unrealistic to deny that there could ever be some sort of nuclear energy or antimatter annihilation fueling, which would clearly be far more efficient. And I should mention also that for some purposes, when you want to launch a small spacecraft within the solar system, there's an idea of having lasers on the ground, which can push against a sail attached to the spacecraft. And of course, if you don't have to carry the weight of the fuel with you, if that's on the ground, that also speeds things up. So I certainly think that for small satellites, there will be the possibility of having faster journeys to the outer planets than we could if we just depended on a rocket.
Thank you, Martin. We have a concern expressed by Paul that the first human on Mars will inevitably and irreversibly contaminate the surface with microbes. Therefore, significant and urgent biosignature and life detection robotic missions are needed fast. Yet NASA has concentrated on geology since Viking. Why is that, and what can be done to expedite?
Yes. Well, I mean, I think this is an important concern, that we don't want to contaminate Mars, because there may have been life on it once, there may be relics of it, and active searches are being made by the probes like Perseverance. And so we do have to be very careful. And of course, if we found that there was some life there, we'd have to be even more careful. But in any case, we've got to treat Mars like the Antarctic and be very careful not to exploit it. And of course, we're aware that if there was some organic stuff on Mars, bringing it back to Earth can be a bit of a danger. So I think we've got to be mindful of all those concerns. But I don't think that should stop us from envisaging that we can explore the surface of Mars and even send a few crazy high-risk takers there, paid for by billionaires.
Thank you, Martin. Question about, in your opinion, which of the planetary bodies in our solar system has the best potential for harboring life between Europa and Enceladus, and why? Yes.
Well, I mean, let me say I'm not an expert at all in this, but I think that looking under the ice of Enceladus, moon of Saturn, or Europa, moon of Jupiter, is an obvious idea, and it's good that people are talking about probes of this kind, robotic probes, which would be able, in principle, to do this within the next 10 or 15 years. And this would be crucially important, because if we were to find evidence of any life of any kind there, then it would tell us that the mystery of how the first life arose, which I said we don't understand at all on the Earth, going from the complex chemistry to the first living reproducing entities, it would show that that was not a rare fluke. And if it had happened independently twice in our solar system, that would immediately tell us that it would exist in a billion places in our galaxy, and our galaxy would be teeming with life. And that would be a huge conclusion. Now, I think going to Jupiter or Saturn's moons is important, because if we find similar evidence for life on Mars, that would be exciting. But of course, there's been a lot of study of whether we could all be Martians, in the sense that life could have started on Mars and then come on an asteroid to the Earth. So if people found evidence for some organic material on Mars, I think it wouldn't clinch the case for two independent origins of the solar system. Whereas I think with much greater conviction, you could say would clinch it if you found something orbiting Saturn or Jupiter.
Thank you. William has said, oh, I seem to be echoing here, I'm not sure why. You mentioned manufacturing in space and the fact that probes to the planets arrive with detectors and rovers a decade or more out of date. What do you see as the prospects in the near term of sending small factories on interplanetary probes and manufacturing the landers, orbiters, etc., with up-to-date technology as the probe approaches the target planet? Or would the required manufacturing be far too complicated?
Oh, that's interesting. Then you gain the length of the journey time, wouldn't you, in terms of update technology? I hadn't thought of that. I mean, if we were thinking about, and certainly the software can be adjusted, I suppose, when it gets there. But I wouldn't ask about that. But as regards manufacturing in space generally, and the technology of space, then of course the space station, although I rather derided its value for money, has done some things in crystal growing and things of that kind. And there may be kinds of experiments that can be done better under zero G when the cost comes down. As regards big structures in space, then obviously we would like to have huge telescopes in space. And incidentally, one thing which I forgot to mention in my talk when I talked about observing an exoplanet is that it would be wonderful if we had a telescope in space, which would have to be a huge interferometer, which could actually detect an exoplanet not just as a point of light, but get the resolved image of it. That's a big challenge. You need an interferometer hundreds of miles across. But I say in my book that this should be a target for 2068. I say that because that's with the centenary of the Earthrise picture, which I showed at the start of my talk, which was inspirational for environment movement. And if we could, 100 years from now, have an image that we could stick on our wall of a planet outside our solar system with life on it, that would be a wonderful new inspiration. So that's a digression. But as regards using space technology, then clearly, if robots can assemble structure under zero G, they can be very lightweight, etc. And the idea of getting solar energy from space, this I used to think was crazy, and it was proposed in the 1970s by someone called Glaser, and it seemed rather crazy. But now I looked into the new data, and it's not that crazy to have a solar energy collector in space and then convert the energy into a beam of infrared and get it down to the Earth. Because in space, you get on average 10 times as much power per square meter as compared to even a sunny place in a desert on the Earth. And you've got to bring it down, but taking that into account and taking account of the fact that the new launchers can launch up to 100 tons at a time and are reusable and therefore cheaper, means that the idea of massive solar energy collection from space is no longer completely crazy.
Thank you, Martin. I think our time has run out for questions. There are many more, so maybe we will be able to have you back at a later date to give another lecture and have more discussion, because it's clearly provoked much interest. So it just falls for me again to thank you, Martin, for a wonderful talk on such an important topic. And to thank all our participants for taking the time to come and join us, and to remind them that we will be, this was the last in our current series, but we will be having a new series of public lectures in October, so watch this space. Thanks again, and have a very good summer, everybody. Thank you. Goodbye.
Thank you.